It's time for a physics project. So I don't know if you've seen this stuff, but this is this race between a Tesla Cybertruck and a Porsche 911, and the Tesla was supposed to win while pulling a 911, and I've talked about that before. But Motortrend did a great analysis, and I really love it. They tried. One of the issues was in the commercial that they made, they only went like an eighth of a mile instead of a quarter of a mile or something like that. I don't really know, and I really want to just look down here at how do we model the motion of a drag race. Okay, so if you come down here, I want to show you what I want. And I'll link to this below so you have it. So here's a plot of distance versus time for both of the objects. And what I want to do is a whole bunch of stuff. Number one, I want this data. Okay, so we're going to take this graph and we're going to get it into Python. After that, I want to build a physics model that reproduces this. And so we're going to have to use some older physics. I'll show you this paper in a little bit to do that. But let's just get started. Okay, so I have a picture of the data. I don't have a 911. Okay, I have a bike. I have a 2001 Toyota Tacoma truck. Okay, I don't have a Porsche. So I don't have the ability to get this. I don't have a quarter of a mile track either. Okay, so this is a picture. I can take that picture. And I've already there's a couple of things which you want to look for are web graph digitizers. So this takes a picture of a graph and you can mark the points and find out the data of the graph. This is not the one I used. I used a different one, but it wouldn't allow me to make it small enough so it fit in my limited area here. So I'm going to use this one. I think it's the same thing basically. So the idea is you want to mark points on both the two axes so it can scale it, and then you mark points. It's a lot like video analysis where you mark points on the graph to get the data. Okay, so let's proceed. It says click the 4 points on the axis in the order shown. 2 on the x-axis, 2 on the y-axis. So let's proceed. So I'm going to come down here, and we don't have to be exact, but you'll do notice that it gives me this little zoomed in window over here. So I'm going to click right there as well as I can. Click. And then I'm going to click X2. I'm just going to go down here to 10. So I'm at 1 and 10. And you got to say click. Okay. Now I'm going to do the Y's. Let's do 100. Yeah, and you can tell I have trouble seeing. 100 and 1,000. 1,200. Okay. That looks good. Continue. Okay, so the x-axis point 1 we did was 1 and 10. And then on the y-axis I did 100 and 1,200. Okay, so now we're ready to start adding data points. I'm going to get the data points for the Porsche. This is position versus time for both the Porsche and the Cybertruck. So we're already on add points. So what I'm going to do down here is just go down here, and I'm just going to start clicking. See that little dot? Click. I'm going to skip every other dot, I think. Otherwise, it's going to be too many dots. And it doesn't really matter because I'm not going to finish it because I already did it. You know I already did it. Dot. No one wants to see me say dot 1,000 times. Dot. 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 Okay. So you see how that goes. And then I can go to data. No, let's see. Where do you just show the data? View data. And there's my data. And then I can copy and paste that into Python. And I already did that. Okay. Now, I want to paste it into WebVPython as a list, and so that's what I did. So let me show you. I already did that. You know, I like to do things live, but I already did that. So let's look at what I already did. Okay, let's make this a little bit bigger. You know, I like everything to be big. Maybe good. That's good. Okay, and then we can maybe make this a little bit bigger too. So I have 2 lists. This is my distance time. I called it TD because I'm going to make another variable. So these are all my time values right here. It's just a giant list of a comma list of all the values. And then I have my X values right here. Those are all my values. And then I have the link. And so what I need to do, the first thing I need to do is I need to go through each of my x values because they're in feet, and I don't like feet, I like meters. So I need to convert those to meters. So I went through the range of x values, and for each x value, I multiplied it by 0.30848 to now it's in meters, okay? And now one other thing that we want to do is to say print the length of x, and I'm going to print the length of TD. And this is just to make sure I didn't make a mistake in my import, because if they don't have the same length of these two lists, I'm going to be in trouble. Okay, they're both 103. That's good. Okay, so let's go ahead and just plot this data. That's what I want to do. Let me see what I did this before. Okay, yeah. So I'm just going to plot the data. So I need to make a graph. G1 equals graph. Let's put title equals Porsche. Is that how you spell it? 911. X title. I should say quarter mile. I'm not going to say that. X title is going to be time in seconds. Y title is X in meters. And now you know I like to make things a little bit smaller, so let's give it a width of 500, a height of 250. And now I'm going to make my first graph. I'm going to call it just F1. G-curve, color equals color dot blue. Now I want to go through all my data points and plot everything. So to do that, I can just say, I want to go through, I need to index the whole thing. So I'm again going to use this indexing thing for I in range, the length of X or TD. It doesn't matter, they're the same length. Range, length, okay. And then I'm just going to plot a data point, f1.plot. My X coordinate is going to be TDI, right? The ith element of the list TD, and then my other one's going to be XI. And that should work. But you never know, it might not work. It worked. Okay, so we have successfully reproduced the data, and it's even then too big. Let's make that a little bit smaller. 400, 200. Okay, good, nice. There's your data. Okay, so now I'm going to go ahead and enter, let's talk about the two models. So let me switch over here. Now that we have that, I should save it. Okay, now to the computer. This is a paper on the physics of drag racing, and it's old. I mean old, 1972. Okay, that is old. It's from the American Journal of Physics. Okay, but let's just make 3 models for a drag race car. And by drag race, I mean a normal street car. Okay, so here's my simplest model. I have the road right here. And then I have my car. And it's going to accelerate that way. So what forces are acting on this car? And again, simplistic model. If you want a very complicated model like front wheel drive versus rear wheel drive, I have a video on that. And if you want it, let me know. I'll post a link on it down below. But in this model, I have 3 forces. I have the downward gravitational force, mg. I have the upward normal force, n. And then what makes the car accelerate this way is the frictional force, F. Okay, so that is important. The frictional force has to make the car accelerate. The model for the frictional force says it depends on the normal force. So the frictional force, the magnitude, is technically less than or equal to the coefficient of friction times the normal force. And for tires on a road, you know, I put about 0.7 for the coefficient of static friction. Now, if you get a real drag race car, you can get crazy high values of the coefficient of friction. But this is real cars, okay? Now in the x direction, in the y direction, F net in the y direction is going to be equal to n minus mg. That's equal to 0. So n is equal to mg. That's important to talk about later. I will talk about that later. Now I can use that value of the normal force and plug it in here to get the frictional force. And then in the x direction, F net, in the x direction, I get the frictional force, which is equal to mu times the normal force, which is mu mg, and that's equal to ma. So you see I can get the maximum acceleration. A max is going to be equal to the coefficient of friction times g. That's my maximum acceleration. Now, if you have a heavier car, like a Cybertruck, yes, you have a larger frictional force. However, you also have a larger force you have to accelerate. Okay, so this is my constant acceleration model. Let's just say that I know the mass of the car, which it doesn't really even matter, and I know the coefficient of friction, I know the value of g, 9.8. Let's just model this. And again, we're going to use our standard model. It doesn't even matter. We're going to calculate the acceleration, and then we're going to say update the velocity, and then update the position. Okay, it's not the best model, but it's going to be fine. It doesn't really matter because we're making the assumption that we're using this final velocity as the average, but we're going to have a short time interval so we can just do it a bunch of stuff. So let's go ahead and make that graph, and then we'll make another graph. Okay, so switching over to here, let's go ahead and enter the data that I have, just because we're going to need that later. I do feel like this might be a tad bit too small. Too big. I think that's good. Okay, so let's go ahead and we have all that. I'm going to put in my mass. I looked up the mass of the Porsche, and it's about 1,500 kilograms. It depends on, of course, who's sitting in it. It depends on how much fuel is in there and all that stuff. The coefficient of friction, I'm going to say is 0.7. I'm going to need the power later, but the one thing I do want is X final is 403. So that's a quarter of a mile in meters. I don't even know how many quarter of a mile is in feet, so I had to look that up. Okay. Now I need time is 0, dt is 0.01. Oh, I need 0.1. I need the g, 9.8. Okay, we're ready to go. So x equals 0, v equals 0, a equals mu times g. And now I can just say while x is less than x final, then I don't need to calculate the acceleration, it's constant. I just need to update the velocity. V, I guess I should call this VF and XF for friction. VF equals VF, because I'm going to add more V's, plus A times dt, and then I'm going to update my position. XF equals XF plus VF times dt, and now I need to update time. T equals T plus dt, and then I need to make a graph, so I didn't do that up here. Let's put a label. Label equals data. F2 equals G-curve. Color equals color dot red. Label equals friction. It's just friction, okay. So now I can plot that. F1, F2 dot plot. I'm going to plot T and XF. And it shouldn't be a very big surprise here. I mean, it's just constant acceleration. And didn't even plot it. Oh, I see what I did. I didn't change this to XF. Yeah, so this is a constant acceleration. The friction data is a parabola. And if you had just constant friction, your acceleration would be greater than that from the actual data, right? Let's go ahead and make a graph of velocity versus time too. Oh no. No, I think I'll just wait for that because my data is in position versus time. I can make a velocity versus time graph. Is that what I did before? Let's see. Let me see what I did before. No, it's just that. Okay, cool. So that doesn't give me the same answer. Now what we can do next is to make a separate model, a constant power model. Okay, switching back to the board. So in this paper, the idea is that, can you read that? Quick, get it. I'm I'll put a link to this. I'm not sure if you'll get it or not because it might be behind a paywall, but it's not easy, not hard to find. The idea is in the paper that a car has some power, right? The Porsche has a power output of 379 horsepower. And if you imagine why doesn't the car keep speeding up with friction, it's because the later times the same amount of power has the same amount of change in kinetic energy. But since kinetic energy is velocity squared, that means you get less and less increases in kinetic energy, in velocity. Okay, so let's look at the power model. Let's plot what would it look like if you had a constant power, and then we'll plot what happens if you have constant power, but you are limited by your maximum frictional force. And I'll show you why. Okay. So constant power model, I have the Porsche 379 horsepowers. I converted that to watts. You know why. You know why I converted that to watts. So in the constant power model, I can again break this into short time intervals. It's not a trivial problem, right? But if I say power is the change in kinetic energy with respect to time, and that's constant. Okay, so in each of these time intervals, I can use that to calculate the change in kinetic energy. So I could write this as K2 minus K1 over delta T. So K2 is K1 plus P delta T. But then I'll need to calculate the velocity. So this is 1/2 m v2 squared equals, let's just say K1 plus P delta T. And then I just need to multiply by 1/2, divide by the mass, and take the square root. So I get V2, the next velocity, is the old kinetic energy. I guess I should put in 1/2 m v1 squared, because I'm going to have that. 1/2 m v1 squared. So if I multiply that and take the square root, I get the square root of v1 squared, because this cancel, plus 2p delta t over m. So if that's constant, I can calculate the new velocity at the end of each time interval and plot it, and that's what we're going to do. I have my mass, I have my power. I didn't put the power in there though. Let's put the power in there. Switching, I have to say switching. I like to do that. Okay, so let's make a third graph. F3 equals G curve, color equals color dot purple. Label equals, I'm just going to call it power. Now I need some more variables too, right? I need my power. Let's just put it down here at the end. So power is 2.79 times 10 to the 5th. I got the mass. Now I need my x and my velocity. So let's call this xp and vp. So those are my velocity variables. So down here, I'm going to, I guess, I should just do a new loop. While xp is less than x final. So the first thing I'm going to do is to update my velocity, right? So that's this equation right here. Vp equals square root Vp squared. Right, that's the velocity before it, plus 2 times m times p times dt. No, divide by m. Yep, okay. So now I've updated the velocity. Now, how do I update the position? What did I do before? Oh, it's the same thing, right? Once I know the position, the velocity, I can update the position with the same rule. So xp equals xp plus vp times dt. And then I need to update time. T equals t plus dt. Oh, you know what? Down here, I need to reset the time. T equals 0 before the next loop. And then I can plot it, f3 dot plot t xp. Let's see what it looks like. Okay, so you'll see here this purple curve is indeed faster. Now in this case, I think I do need to plot. I want to plot the velocity versus time for the constant power so you can see the problem. So let's just make a second graph down here. G2 equals graph. You can do that. Title equals Porsche. Is it CH? I don't know. 911. I obviously don't have a Porsche. X title equals time. Y title equals velocity in meters per second. And then I need my same width. Width, I don't have to, but width equals 400. Height equals 200. And let's make a graph called FPV for power velocity. G curve color equals color.blue. Now down here I can plot, but no, if you have more than one graph and more than one function, you can tell it what graph to plot it in. But if you do it in order, these are going to plot on all the graphs above it, and then if I make a new graph, anything below that's going to plot on that one. Just a little tip for you there, a web v Python tip. So down here, what did I call? I'll call that fvp.plot t vp. And something happened. FPV, and I called it FVP. So which one? FPV, FPV. Okay, so there's the velocity as a function of time, and maybe you can see the problem. Look at the acceleration. The acceleration is the slope right here, and it's like essentially infinite right at the beginning, right? If you have a constant power, you're going to get an infinite acceleration in that very short time interval because you're going from 0 to whatever. And you can see we do have a vertical slope right there, and that's not allowed. Okay, so how can we fix that? What we want to do is to make a new model that says it's constant power as long as that change in velocity is less than the frictional one. And I'm just going to change. I'm not going to make a fourth graph one here. I'm just going to change it. So up here, I guess we can combine these two together. Let's combine these together. And I don't want two time updates. Okay, so now I'm in one loop calculating everything together. And I'm going to, let's cut this. And let's cut all this stuff. Let's cut this, put this up at the top. I want to calculate the frictional velocity first. And now, and the power velocity. So I guess I do need a third velocity. Let's call it Vm. Yeah, I'm just going to call it for the model. Okay, V model. So I calculated my velocity through two different ways, and I'm just going to pick the smaller of the two. So if VF friction model is, what did I do before? If VF is greater than, the friction model is faster than VP, then I'm going to go with VP. So Vm equals Vp. Else, Vm equals Vf. That's good. And then I need to update the position. Let's do that as, let's call this Xm. And then down here, I'll just update the position. Xm equals Xm plus Vm times dt. Okay, and then I'm plotting the constant power. Let's just change that to Xm. And let's change this too. Okay, I think it'll work. I got a little sloppy there, I admit. Okay. So the friction data is way higher than these two. That's the actual data. Notice these two are close. Let's get rid of that friction data, just so I think it's skewing. It shows you how much faster the thing is. Let's not plot that. So let's not plot the friction, which is right here. So we just have those two. Okay, so you can see that it looks a lot better, and there's that point where it switches over. I like that little jink right there. So what we can do is we want our model is a little bit fast. So we can change our power output. I want to have a lower power output because that's a listed power, but we're some energy is going into rotating the tires, some energy is going into rotate the engine RPMs. There's of course air drag. I did not include that. That's a homework assignment. So let's just change the power. Let's just say this power is, let's say, 0.9 times, 90%. Decrease the power by 90%. Okay, let's decrease it to 80%. I'm just playing it around, right? We can do that with a model. And you can see I'm getting really close. As long as I can get it to match the data, that's pretty good, right? Now maybe I want to increase my friction a little bit, but you can play around with this forever. But I'm getting really close to matching those two things. And you can imagine that if I play around with this enough, I could get it to match. I mean, I'm pretty happy with that. Okay, so this idea of a constant power model for cars seems to be realistic. At least we can make it match real data. Now, I do want to show you one more thing, and that's what if you had super great power? Electric cars can have super great power, but you want to overcome that friction problem. Well, there is one trick, and if you haven't seen this, it's pretty cool. Okay, so over here, I have my car. Suppose I have as much power as I want. Well, I can only accelerate along with friction, right? Friction's my limiting factor. However, there's a cheat. And what these newer cars do, they cheat by having an extra force pushed down in the vertical direction. Usually this is with like a fan or suction under the thing. So this pushes it down more without increasing the mass. So now in this case, if I push down with some force Fp, then back to my F net y equation, F net in the y direction, I have Fp, no, I have N minus Fp minus mg equals 0. So now N is equal to Fp plus mg, and the frictional force is going to be mu times Fp plus mg. So I can increase the frictional force without increasing the mass, and that's the key. That's what allows some of these electric cars to have crazy high accelerations, right? Because you can increase the friction to whatever you want. Note that actually also increases the friction so you can stop with a greater acceleration. You could turn with a greater acceleration. In fact, they do make some remote control cars that use this and can drive up a wall, right? Because now what pushes you against the wall is a fan, a motor, and it makes a friction. So there you go. Okay, but that wasn't the point of this video. It was to build a model of an accelerating Porsche. Hope you enjoyed that. I'll put links down below. If I forget something, just leave me a comment. If I made a mistake, good job catching it. I do make mistakes. Talk to you later.